Welcome! Today, we'll dive into an exciting and challenging problem, LeetCode number 1202, smallest string with swaps. Together, we'll explore various approaches to solve this problem efficiently. Let's get started. In this problem, you are given a string S consisting of lowercase English letters, and an array of pairs, where each pair specifies two indices in the string. These indices indicate that you are allowed to swap the characters at those positions as many times as you want. Your task is to determine the lexicographically smallest string that can be created by applying these swaps. The input includes the string S and the list of index pairs, while the output is the lexicographically smallest version of the string after performing the swaps. For example, if you think of the alphabet in its natural order, A comes before B, B before C, and so on, so the smallest string is the one that follows this order as much as possible. Let's explore some examples to clarify this further. Take the first example, where the input string is S equals tab and the list of pairs is pairs equals 0, 3, 1, 2. Here, you are allowed to swap the characters at indices 0 and 3, as well as indices 1 and 2. Initially, the string is tab. Using the pair 0, 3, you can swap the characters at these positions to transform the string into CAD. Then, using the pair 1, 2, you can swap characters at those indices to get backed. This is the smallest possible string that can be obtained by applying these swaps, so the output is backed. Notice how we focused on rearranging the characters to make the string as small as possible alphabetically. Now, consider the second example where S equals tab and the pairs are pairs equals 0, 3, 1, 2, 0, 2. Again, you start with the string cab. Swapping indices 0 and 3 gives CAD, and swapping indices 1 and 2 updates it to backed. Finally, using the pair 0, 2, you swap the characters at those positions to get ABCD. This string is lexicographically smaller than any other possible arrangement, so the output is ABCD. This example shows how additional pairs can allow for more flexibility in rearranging the string to achieve the smallest possible order. In the third example, the input string is S equals CBA with pairs equals 0, 1, 1, 2. Starting with CBA, you first swap indices 0 and 1 to get CA. Then, swapping indices 1 and 2 results in BAC. Finally, you swap indices 0 and 1 again, which transforms the string into ABC. This is the smallest possible arrangement of the string, so the output is ABC. This example highlights how multiple swaps, even involving the same indices, can be used to gradually refine the string into its smallest lexicographical form. When solving this problem, it's important to consider a few key edge cases. First, if the pairs array is empty, no swaps can be performed, so the output is simply the input string S. For instance, if S equals ABC and pairs equals, the result is ABC. Second, if the string contains only one character, the output will always be that character, regardless of the pairs array. For example, S equals A and pairs equals 0, 0, will result in A. Another case involves disconnected swaps, where groups of indices are not interconnected. For example, with S equals cab and pairs equals 0, 1, 2, 3, each group of indices is sorted independently, resulting in ABCD. Finally, given the constraints, ensure your solution is efficient and can handle large input sizes, where the length of S and the number of pairs can go up to 100,000. Efficient handling of these scenarios is crucial for solving the problem within the given limits. To solve the problem of constructing the lexicographically smallest string by swapping characters at specific indices, we can consider a few different approaches. One naive method is the brute force approach, where we repeatedly swap characters as allowed by the given pairs and check if the resulting string is smaller. However, implementing this means generating all possible permutations of the string using the given swaps, which quickly becomes computationally infeasible as the input size grows. The time complexity in the worst case is factorial, O(n), making this approach impractical for larger strings. A more promising and efficient method is a graph-based approach. Here, we can think of the string as a graph where each index is treated as a node and each pair of indices forms an undirected edge. Using this graph representation, we can group nodes into connected components. Within each connected component, characters can be freely swapped. By sorting the characters in each component and placing them back in their original positions, we ensure the smallest lexicographical order for that group. The process of grouping indices is efficiently handled using union find, also known as disjoint set union, DSU. This optimized graph-based approach is both efficient and well-suited for the problem's constraints. The optimized graph-based approach has an efficient time complexity that makes it ideal for solving this problem. Using union find to build the graph and determine connected components takes O, n plus m, where n is the length of the string and m is the number of pairs. Sorting the characters within each component is the most computationally expensive step, with a complexity of O, k log k, for a component of size k. By summing across all components, the total sorting cost is bounded by O, n log n. Combining these, the overall time complexity of this approach is O, n plus m, plus n log n. This makes the method highly efficient for large inputs. One alternative to union find is using BFS or DFS to find connected components. While these methods achieve the same asymptotic complexity of O, n plus m, they can involve additional overhead from recursion or queue management, making union find a simpler and more direct choice for this problem. Ultimately, the graph-based approach using connected components is chosen for its computational efficiency and its natural fit with the problem requirements. By grouping indices and sorting characters within each component, we achieve minimal lexicographical order with minimal operations. The key insight in this problem is reducing it to identifying connected components in a graph. By recognizing that characters within the same component can be freely swapped, we can focus on rearranging these groups to minimize the lexicographical order. Sorting the characters within each component is the critical step that ensures the smallest possible arrangement. While the union find approach is efficient, it's important to implement it carefully using optimizations like path compression and union by rank. These enhancements ensure that the operations remain nearly constant time, keeping the graph construction and component grouping efficient. Although the sorting step adds an O, n log n, term to the overall complexity, it is unavoidable for achieving the desired order. Ultimately, the optimized graph-based approach strikes the right balance between efficiency and simplicity, making it well-suited for this problem. It effectively handles the constraints and scales to large inputs, ensuring correctness and performance within reasonable bounds. In this problem, we are tasked with transforming a string into its lexicographically smallest form using a set of allowed swaps. Think of each pair of indices as an instruction that allows you to swap the characters at those positions as many times as needed. The key challenge here is to determine which characters can be swapped with one another, and then to arrange them in the smallest possible order. To solve this, we can model the problem as a graph where each index in the string is a node, and each pair of indices forms an edge between two nodes. The connected components of this graph represent groups of indices that can be freely swapped among themselves. This is the key insight. Within each connected component, we can rearrange the characters at those indices to form the smallest possible subsequence. To effectively manage these connected components, we'll use the union find data structure, also known as disjoint set union, or DSU. To build the connected components, we use the union find data structure. This allows us to group indices into clusters where swaps are possible. The process begins by initializing a parent array where each node is its own parent. This means that initially, every index is considered its own separate component. We then define two essential functions: find, which helps us locate the root or leader of a node, and union, which merges two components by connecting their roots. The find function also uses path compression to ensure that subsequent operations are faster, while the union function can be optimized further with techniques like union by rank or size. After defining these functions, we iterate over each pair of indices given in the input, using the union function to connect the two indices. By the end of this step, all indices that belong to the same connected component will share the same root. To organize these components, we use a dictionary where the root of each component serves as the key, and the indices belonging to that component are stored in a list. For example, if indices 0, 3, and 5 are connected, they will be grouped together under the same root in the dictionary. Once we have identified the connected components, the next step is to extract and sort the characters within each component. For every connected component, we look at the indices it contains and retrieve the corresponding characters from the string. These characters are then sorted lexicographically to ensure the smallest possible arrangement. After sorting, we reconstruct the string by placing the sorted characters back into their respective indices. This involves iterating through the indices of each component in sorted order and assigning the smallest available character from the sorted list. By doing this for all connected components, we ensure that the rearranged string is as small as possible in lexicographical order. Finally, the modified string is returned as the result. This approach guarantees correctness because each connected component is handled independently, and within each component, we prioritize the smallest arrangement of characters. The key insights from this algorithm are rooted in the graph representation and the efficiency of union find. By modeling the indices as nodes and the allowed swaps as edges, we simplify the problem into identifying connected components. The union find data structure is particularly well suited for this task, as it allows us to dynamically merge groups and find their leaders in nearly constant time, thanks to path compression and union by rank. Additionally, sorting the characters within each component ensures that we achieve the smallest possible arrangement for the final string. In terms of data structures, the union find is critical for grouping indices, while a dictionary helps us efficiently organize the indices of each connected component. Together, these components enable an elegant and efficient solution to the problem. Handling edge cases is crucial to ensure the robustness of the algorithm. For instance, if no pairs are provided, the string is already in its lexicographically smallest form since no swaps are possible. Similarly, indices that are not part of any pair form single-node components and remain unchanged. When there are multiple connected components, each must be processed independently to ensure correctness. Duplicate pairs in the input do not affect the algorithm's behavior, as union find inherently handles redundant connections. In terms of complexity, the union find operations are highly efficient, with an amortized time complexity of O(n*alpha n), where alpha is the inverse Ackermann function. Sorting the characters within each component contributes O(n log n) in the worst case, resulting in an overall time complexity of O(n log n). The space complexity is O(n), accounting for the parent array and the dictionary used to group indices. This balance of efficiency and clarity makes the algorithm well suited for solving the problem. To solve the problem of finding the smallest string with swaps, we use a union find data structure. First, we define two helper functions, find and union. The find function helps locate the root of a given node, and it uses path compression to optimize future queries. The union function connects two nodes by merging their roots. Next, we initialize the union find structure. Since each character in the string is initially its own component, we create a parent list where each index is its own parent. Then, we use the given pairs to build connected components. For each pair, x, y, we call the union function to link the two indices, ensuring that all indices in the same connected component are grouped together. Finally, we create a default dict to organize the characters into their respective connected components. For each index in the string, we find its root using the find function and group the index under the corresponding component in the dictionary. Once the connected components are built, we append the indices of each component to the component's dictionary. Converting the string S into a mutable list allows us to modify it efficiently. For each group of indices in the component's dictionary, we retrieve the characters corresponding to those indices and sort them lexicographically. Similarly, we sort the indices to ensure the sorted characters are placed back into the string in the correct order. Using a loop, we then zip the sorted indices and characters together and update the string S by placing each character at its respective position. After processing all the components, we join the list back into a string and return the result. This ensures that the smallest lexicographical order is achieved for all connected components in the string. To solve the problem, we begin by implementing the union find data structure, which is a key part of this solution. The first step is to initialize an array called parent that will track the parent of each node. Here, each node is initially its own parent, which means each element in the array is set to its own index. Next, we implement the find function, which determines the root parent of a given node. This function uses path compression to optimize future lookups by ensuring that all nodes in the path directly point to the root. Finally, we define the union function, which connects two nodes by assigning one root as the parent of the other. This ensures that nodes in the same connected component share the same root parent, which is essential for grouping indices together later in the solution. Now, we use the union find data structure to build the connected components. By iterating through each pair in the input list, we call the union function to group the indices that can be swapped. Once we've established these connections, we map indices to their root parents using a hash map. Each key in the map represents a root, while the associated value is a list of indices belonging to the same connected component. After creating this mapping, we prepare to reconstruct the smallest possible string. First, we convert the input string into a mutable character array, which allows us to modify it directly. Then, for each connected component, we extract the characters at the indices, sort them, and also sort the indices themselves. This ensures that the smallest characters are placed in their correct positions within the component, giving us the lexicographically smallest arrangement. Finally, after processing all the components, we convert the modified character array back into a string and return it as the result. This string represents the smallest lexicographical order that can be achieved by swapping characters according to the given pairs. The solution is efficient because the union find operations, along with sorting and mapping, are carefully optimized for performance. This concludes the implementation, ensuring that all components and their characters are properly organized to meet the problem requirements. To solve this problem, we start by initializing a union find data structure. Here, the parent array is 0, 1, 2, 3, meaning each element is its own parent initially. Next, we perform union operations based on the given pairs. For the first pair, 0, 3, we find that the parent of 0 is 0, and the parent of 3 is 3. Since they have different roots, we unify them by updating parent 0 to 3, resulting in the updated parent array 3, 1, 2, 3. For the second pair, 1, 2, the parent of 1 is 1, and the parent of 2 is 2. Again, we unify them by setting parent 1 to 2, giving us the final parent array 3, 2, 2, 3 for this step. Now that the union operations are complete, we group the indices into connected components based on their roots. For index 0, the root is 3, and for index 3, the root is also 3, so they form one component, 0, 3. Similarly, indices 1 and 2 share the root 2, forming the component 1, 2. This gives us the components 3, 0, 3, 2, 1, 2. Once we have the components, we sort the characters within each group. For the component 0, 3, the characters are D, B. Sorting them results in B, D. We then place these sorted characters back into their respective positions in the string, updating S, 0, to B and S, 3, to D. The string becomes cat at this stage. For the second component, 1, 2, the characters are C, A. Sorting these gives A, C. We place these sorted characters back into the string, updating S, 1, to A and S, 2, to C. The string now becomes backed. With all components processed, the final output for this example is backed. Moving to the second example, the input string is tab and the pairs are 0, 3, 1, 2, 0, 2. We start again with a union find data structure, initializing the parent array as 0, 1, 2, 3. For the first pair, 0, 3, performing union results in the parent array 3, 1, 2, 3. The next pair is 1, 2. Performing a union here updates the parent array to 3, 2, 2, 3. For the final pair, 0, 2, we first find the root of 0, which is 3, and the root of 2, which is 2. Since these roots are different, we unify them by updating parent 3 to 2. The updated parent array is 3, 2, 2, 2. Now, we group the indices into connected components. All indices share the same root, 2, so they form a single component, 0, 1, 2, 3. The components are represented as 2, 0, 1, 2, 3. With the components identified, we now sort the characters within the single component, 0, 1, 2, 3. The characters corresponding to these indices are D, C, A, B. Sorting them gives A, B, C, D. We then place these sorted characters back into their respective positions in the string. Updating S, 0, to O, S, 1, to B, S, 2, to C, and S, 3, to D, the string becomes ABCD. This gives us the final output for this example, which is ABCD. In the third example, the input string is CBA and there are no pairs provided. We initialize the union find data structure with the parent array 0, 1, 2. Since no union operations are performed, each index remains its own component. The connected components are 0, 0, 1, 1, 2, 2. As there are no connections, no sorting is needed within the components. The string remains unchanged as CBA, which is the final output for this example. To analyze the time complexity of our solution, we break it down into individual steps. First, initializing the union-find data structure involves creating a parent array of size n, where n is the length of the string. This takes n time. Next, we perform union operations for each pair in the pairs array. Each union operation consists of two find operations, and with path compression, the amortized time complexity of each find is alpha n, where alpha n is the inverse Ackermann function. This function grows so slowly that it's effectively constant in practice. For m pairs, the total time for all union operations is m asterisk alpha n. Finally, we need to determine the connected components by performing a find operation for each of the n indices in the string. Since each find takes alpha n, the total time for this step is n asterisk alpha n. Now, let's look at the cost of sorting the characters within the connected components. For each connected component, we sort the indices and characters. If the sizes of the components are denoted as C_1, C_2, C_k, and their sum equals n, sorting each component individually takes C_i asterisk log, C_i time. When we sum this cost over all components, the total complexity becomes n asterisk log n, as sorting dominates. Once sorted, we reconstruct the string by placing the characters back based on their indices. This step involves a linear traversal of all components, which takes n. Combining all these steps, the overall time complexity becomes n plus m asterisk alpha n plus n asterisk alpha n plus n asterisk log n plus n. Simplifying, we get m asterisk alpha n plus n asterisk log n. Since alpha n is nearly constant, the time complexity is effectively m plus n asterisk log n for most practical purposes. Turning to space complexity, the union-find data structure requires a parent array of size n, resulting in n space. We also need to store the connected components, which are stored in a dictionary where each key maps to a list of indices in the same component. In the worst case, all indices could belong to a single component, requiring n space. Additionally, temporary arrays are used to store characters and indices while sorting each component. Across all components, this requires space proportional to the size of the string, which is n. Finally, since strings are immutable in Python, we convert the string s into a mutable list representation, which also takes n space. Combining all these, the total space complexity is n. When comparing approaches, a brute force method would involve generating all possible permutations of the string by applying the given swaps and checking the lexicographical order of each permutation. This would result in n permutations in the worst case, leading to an infeasible time complexity. The space complexity would also be enormous, as we'd need to store all permutations. In contrast, the optimized union-find-based approach focuses on identifying connected components, which drastically reduces the scope of work. Its time complexity is m plus n asterisk log n, and space complexity is n. This is orders of magnitude better than the brute force method, making it far more practical and efficient. Analyzing the best, average, and worst cases gives us a better understanding of the solution's performance. In the best case, where there are no pairs, m equals 0, the string is returned as is, and the time complexity simplifies to n. In the average case, the complexity remains m asterisk alpha n plus n asterisk log n, as it depends on the structure of the input. The worst case occurs when all indices belong to a single connected component, requiring sorting a single array of size n. Even in this case, the complexity does not change and remains m plus n asterisk log n. This consistency across cases highlights the efficiency of the union-find-based approach, which is designed to handle large inputs optimally in terms of both time and space. When working on this problem, there are several common pitfalls that can hinder your solution's efficiency and correctness. First, it's crucial to use union-find efficiently by incorporating path compression and union by rank. These optimizations ensure that the operations run in nearly constant time, which is essential for handling large inputs. Without these, you're likely to encounter time limit exceeded errors. Another frequent mistake is sorting the entire string instead of just the connected components. Sorting the entire string unnecessarily increases the time complexity, while sorting individual components keeps the solution more efficient. You should also take care to handle edge cases, such as when the graph has disconnected components. Neglecting to account for these can lead to incorrect results or runtime errors. Be mindful, too, of how you interpret lexicographical order. Always sort characters as strings, not as numbers. Finally, if you're using DFS or BFS for graph traversal, make sure to track visited nodes to avoid redundant computations, which can further slow down your solution. Now, let's consider some insights that are particularly relevant in interview scenarios. This problem is a textbook example of using union find, so interviewers often expect you to demonstrate not only its implementation but also its optimization with techniques like path compression and union by rank. It's also important to recognize this problem as a graph problem, where nodes represent characters and edges represent the swap operations. Emphasizing your understanding of connected components is key. Solving the problem by focusing on these components rather than the entire string is a critical insight. Additionally, interviewers may test your ability to handle edge cases, such as strings that require no swaps, fully connected graphs, or cases with multiple isolated components. Beyond this specific problem, it's helpful to recognize related problems that also involve union find or graph traversal. Examples include LeetCode 547, which involves identifying connected provinces, LeetCode 1319, which examines network connectivity, LeetCode 721 for merging accounts, and LeetCode 323, a fundamental problem on counting connected components in an undirected graph. Finally, while union find is the most efficient solution for this problem, there are alternative approaches worth noting. Using DFS or BFS is a viable option for identifying connected components. These methods are often simpler to implement but can be slightly slower than an optimized union find solution. Another approach is representing the graph with an adjacency matrix. While this can make the graph structure easier to visualize, it is highly memory intensive, with O(n)² space complexity, making it impractical for large inputs. It's important to weigh the trade-offs between these methods. Union find offers the best efficiency, with a time complexity of O(n)log n, but requires careful implementation of optimizations like path compression and union by rank. DFS and BFS, on the other hand, are more straightforward to code but may not perform as well for larger problems. The adjacency matrix, while intuitive, is generally unsuitable for large-scale graphs due to its memory demands. Understanding these trade-offs will help you choose the right approach based on the problem's constraints and requirements. Thank you for joining this walkthrough of problem number 1202, smallest string with swaps. We summarized the key steps, highlighted the time and space complexities, and discussed the importance of union find for solving graph-based problems. Be sure to practice similar problems and subscribe for more solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!